Today I'll be talking about how we determine paleolatitude, which is key in the reconstruction of Earth's history. To start off, let's discuss the Earth's magnetic field. Earth acts like a large magnet, with lines of force extending from the South Pole to the North Pole. Without the magnetic field, life as we know it would not be possible, because the magnetic field blocks harmful solar radiation. It is this interaction between the magnetic field and the sun's rays that is responsible for the northern lights. But why do we have a magnetic field? The Earth's interior consists of 4 layers. The uppermost, or first layer, is the crust. Beneath the crust lies the thickest layer, and that is the mantle. Third is the outer core, and finally, the inner core is last. For the purposes of this video, I will be focusing on the outer core. The outer core holds the distinction of being the only liquid layer in Earth's interior. The fact that it is liquid is the reason for Earth having a magnetic field. Though the exact mechanisms for disturbances in the magnetic field are mostly unknown, it is widely accepted that the rotation of liquid iron and nickel in the outer core, as shown here, is responsible for the generation of our magnetic field. So how can we use this in the process of determining paleolatitude? Igneous rock can consist of countless minerals, some of which may be magnetic, such as magnetite or iron-nickel. When these minerals cool and the igneous rock is formed, those magnetic minerals record information about the magnetic field at the time, as well as the latitude at which the rock is formed. We know that magnetic minerals will align themselves with the magnetic field at the time of cooling, as shown here by the black lines being aligned in a perfect north-south orientation. This same process happens in 3 dimensions, with magnetic minerals also having a vertical orientation, known as the dip. The angle of the dip is known as inclination. This is an example of a dip angle that a compass needle would make somewhere in the northern hemisphere. A positive dip angle represents the needle pointing down into the Earth. This occurs in the northern hemisphere. Dip angles roughly follow the magnetic field force lines shown earlier. Here is a world map of inclination values. Positive values are shown in red, and negative values are shown in blue. Using this knowledge, geologists and geographers alike have reconstructed Minnesota's location through time. They have shown us that Minnesota has moved some 3,000 miles since the Cambrian, when it sat just south of the equator.